Okay, in this lecture, I'm going to give you some more details how to derive the current voltage characteristics of PN junction diode. So the corresponding part of your textbook authored by Professor Robert Vieira is chapter 6.1. So before moving forward, please take a look at the note described in this slide. So let me speak it out. Typically, PN junctions in IC devices are formed by counter-doping. So as you have already known, the silicon substrate wafer itself, to minimize the cost for fabricating a single piece of silicon substrate, the P-type doped silicon wafer is the cheapest one. So the basic silicon substrate is P-type doped one. So to implement N-type resin onto the P-type silicon substrate, you should implant more number of donors than the P-type resin has been counter-doped into the N-type resin. Okay, and the equations derived in this class, as well as in the textbook, can be readily applied to such diodes if Na indicates a net acceptor doping concentration on P side. So basically, whenever I'm writing down the n sub A, which means Na minus Nd in the P-type region, and if I'm writing down the n sub D, which indicates the net donors doping concentration on N side, that is corresponding to the n sub D minus n sub A in the N side region. So basically, Na or Nd, that symbol indicates, the most abundant uh, impurity or dopant atoms, in the corresponding region. So Na means always Na minus Nd, but usually donor's concentration Nd is much smaller than the acceptor's concentration of Na in the P side. Okay. Uh, just a few decades ago, it was very tough and challenging for device and process engineer to implement linear step graded junction. So I'm talking about this. So this is the cross-section view of a silicon substrate and say p-type silicon substrate. And on top of it, you want to make an N region. Then we're gonna have a PN junction, okay, here in. But the problem is if I draw the doping profile along the x direction here, so Na minus Nd, then maybe at a certain point to say this is the surface is corresponding to the x of 0, and that is indicates a physical junction of PN diode. Then basically the top side of silicon substrate is N-type and the bottom side is P side. Therefore, if I draw the doping profile, the y-axis is Na minus Nd, then this doping profile is ideal for this PN junction. But the problem is the process engineer cannot make it to fabricate this red colored step doping profile. So for a while, this is the best one in terms of doping profile in PN junction diode. So theoretically, many device engineers and device physicists has studied how to do analysis for the linearly graded PN junction. So for given doping profile for the linearly graded PN junction like this, okay, so this is N side and P side, and near the physical contact area, left hand side and right hand side, instead of a step like junction, this cannot be make it. So this black colored one indicates the realistic doping profile for the linearly graded junction. But as of today, you don't need to worry too much about. Process engineer has made it to make the step-like doping profile in the PN diode. So all this material discussed about linearly graded PN junction can be dumped into the waste box. So you don't need to study anymore. Okay, so in this movie clip, I'm going to focus on the step-like PN junction diode. So a PN junction diode which has a step-like doping profile across the PN diode. So uh, it is the practical and fabricated PN diode is almost identical to the ideal PN junction diode. And herein, let me tell you a few basic assumptions to be used in deriving the current voltage characteristic of the PN diode. So in this lecture note, you can see the some cross-sectional view of PN junction, which is biased by the DC voltage denoted as V sub A here. Okay, so DC bias has been applied to across this PN diode, and a few assumptions are to be used. So herein, the metallic part matter is physically conducted to the P side. So there should be certain amount of voltage drop between matter and P side, but we are gonna neglect it. And we are going to assume that the ohmic contact of MS junction has been well made. On the opposite side, you can see another matter and semiconductor junction, and here in more specifically matter and N side. And we are going to neglect the voltage drop across this MS junction, and definitely we are going to use we are going to assume the ohmic contact has been well provided. Okay, and as we have learned, this p-type silicon, n-type silicon, each of it has its own unique resistivity or conductivity. So just to refresh your memory, the resistivity is defined as the 1 over conductivity denoted as a sigma, and this sigma is defined as unit charge q times electrons mobility times electron concentration plus another unit charge times hole mobility times hole concentration p. Well, definitely this electron concentration would be governed by Nd minus Na, and this hole concentration depending on which material, and either n-type or p-type, you can simply determine the electron concentration and hole concentration. Suppose that this is a p side, then acceptor is much higher than donor's concentration, so that hole concentration is identical to the Na minus Nd, but you can ignore it because the Na is much higher than the N sub D. Then, using the mass action law, N times P is equal to Ni square. So you can derive and you can determine the minority carrier concentration in P side. N is equal to Ni square over P. And here the P is corresponding to the acceptor concentration in the P side. Okay, and just for your information, the N sub I indicates electron concentration when the semiconductor material is intrinsic. So typically at room temperature 300 Kelvin, the N sub I of silicon material is 10 to the 10. Okay, so 10 billion per cubic centimeter. So N sub I, N sub I is 10 to the 10 per cubic centimeter. Um, uh, okay. I have just faced with a technical issue. Sorry about that. Okay, let's keep going. So this P side and N side across the PN diode has its own conductivity or resistivity. So once we know the physical dimension of this PN diode, say, because I have drawn the cross-section view of the PN diode, but if I imagine the full picture of the, three-dimensionally formed PN diode, that looks that looks like as follows. So there is a cross-sectional area and the total length of the PN diode. Definitely the P side length and N side length. Okay, so once you know the length and cross-sectional area, so you're gonna simply derive the resistivity of the P side. That is corresponding to the resistivity times the length of the P side divided by cross-sectional area. So since resistivity rho is non-zero and LP is definitely non-zero, A is non-zero, so LP is non-zero. Therefore, once a certain amount of DC bias has been applied across the PN diode, a certain amount of current is flowing throughout the PN diode. Therefore, the P side itself should, you know, should have a certain amount of voltage drop. However, in ideal diode analysis, which we are going to do, is going to neglect all the voltage drop across P side. Okay, so simply speaking, no voltage drop across P side. Okay, here in no voltage drop. And similarly, no voltage drop across N side. Okay, then the question is which region in the PN junction diode can have a whole amount of voltage obtained from the DC bias here, DC voltage source. So let me erase all the note to clearly show you which region would uh, have all the voltage applied across the PN diode to be dropped. So the answer can be found here. In the depletion region of the PN diode, would experience all amount of voltage applied across the PN diode. So simply speaking, across the depletion region, the voltage drop would be identical to the voltage that you have applied. Okay, so here say junction voltage is almost equal to the VA applied voltage. Okay, all right, and one so that's a key message in this slide. So please remember that the voltage that you have applied is 100% of a voltage that you have applied is well delivered to the voltage drop across depletion region. Okay, in other words, no voltage drop herein and there. Okay, and one more notice and message that I want to say is this: the applied voltage V sub A should be significantly smaller, much smaller than VBI. What is VBI? Yes, built-in potential. So built-in potential VBI is very well associated with the doping concentration of each side, P side and N side. So as we have learned in the last semester, the built-in the portion a part of the built-in potential comes from the P side. And if I write down the equation for that is KT over Q times Ln N sub A, no, Ni over N sub A. So here, this N sub A indicates how much acceptor has been included in the P side. And the other part of the built-in potential coming from the N side is KT over Q times Ln Ni over Nd. I guess I guess I was confused with which one is correct, but I need to double check. Let me see. Ah, there we go. Okay, sorry about that. That should be NA. Oops, what happened to my pen? Okay, NA, and there should be N sub I. ND, N sub I. Okay, so built-in potential is defined as KT over Q times Ln Na times Nd divided by Ni square. Okay, so doping concentration would determine mainly the built-in potential. So usually the typical range of the doping concentration is 10 to the 15 to 20. Then you may guess the maximum and minimum built-in potential across p-n diode. So suppose that the p side is doped with acceptor say 10 to the 16 per cubic centimeter, and n side is n sub d is a 10 to the 16. And then the built-in potential is, you remember the 60 millivolts load that I have taught in the last class. So take a 6 and the 60 millivolt, then 0.36 milli, no, just a electron volt. So the Fermi energy level of the p side is away from the intrinsic Fermi energy level by 0.36. And similarly, the n side is, Fermi energy level is away from the intrinsic Fermi energy level by, 6, so that 0.36 electron volt. So if I consider both of them and sum them up, then the built-in potential is equal to 0.72 volt. So if you're a circuit designer and if you're interested in designing a digital analog circuit, you maybe have a many chances why the constant voltage drop has always been considered across the PN diode. And usually the value is a 0.5 or 0.7 or 0.6 depending on the textbook or depending on the problem sets. Why 0.7? Why 0.5? That number is very closely associated with the doping concentration in PN junction, each side of PN diode. So suppose that the constant voltage drop of 0.7 volt is assumed in a certain problem set across the PN diode, which means P side N side is doped with 10 to the 16 in doping concentration. Okay. All right. So going back to the last message in this lecture slide, the applied voltage VA should be much smaller than built-in potential. Why is that? Why this assumption is necessary? If this assumption is neglected, denied, then, in other words, otherwise, if VA is quite similar to the built-in potential or very almost equal to the VBI, then what would be happened across a PN diode? Yeah, device physics is that is not very ideal one. So whenever we are doing the analysis for ideal, again, ideal PN diode, we're gonna basically assume that the low level injection is dominant. So in the last semester, you had a chance to understand the physical meaning of low level injection. Just for those who didn't have a take my lecture last semester, just the meaning of low level injection is that once a forward bias is applied across a PN diode, forward bias is applied across PN diode, many holes would be injected into the N side. However, the majority carrier of N side is electrons. So the total amount of electrons or the concentration of electrons would not be affected by the injected holes. That means low-level injection is still working. But if too many holes are injected into the N side, and that event would significantly affect the electron concentration or majority carriers concentration in the N side, then low level injection has not been successful. High level injection is working. Okay, so in the upcoming ideal diode analysis, basically we are going to assume the low level injection instead of high level injection. That means once a forward bias is applied, or just simply speaking, the applied voltage VA is applied across PN diode, then you should always imagine that the majority carrier concentration either in P side or N side would not be significantly affected by the carriers injected from the other side. So for example, the holes are now injected into the N side because of the positive bias or higher voltage has been applied onto the P side. However, the total amount of electrons, which is the majority carrier in N side, would not be significantly affected. Okay, so that is the last assumption that I'm going to use in doing ideal PN diode analysis. Okay, so in this lecture note, you're gonna see at a first glance how the energy band diagrams can be drawn under different biasing conditions. So figure A indicates, shows energy band diagrams of PN diode when the voltage is zero. In other words, at thermal equilibrium, the energy band diagram of PN diode has been drawn herein. So as we have learned in the previous lecture, since at thermal equilibrium, a single system should have a unique energy level, unique value of Fermi energy level. So EF is single valued. Okay. So again here, y-axis indicates energy of electron, x-axis indicates a physical distance and physical displacement across PN diode. So EF, this value is very single valued. That means because it is at thermal equilibrium. So this energy difference, EI minus EF, is well associated with the doping concentration on the P side. And here EF minus EI, this energy difference is well matched to the doping concentration on the N side. Okay, and here the band bending has been happened, right? We can use a second order polynomial equation to describe how much band bending has been happened across the PN diode. And here you can see the two different curvatures, and this point is well matched to the physical contact between P side and N side. And as I have told you, the upside direction indicates a built-in electric field across PN diode. Okay, all right. And now let's apply the forward bias. In other words, once a reference voltage has been applied to the on-side, N-side, say 0 volt is a reference voltage, then a certain voltage higher than reference voltage is applied to the P side, which means a forward bias has been applied. So usually positive bias has been applied, which means a forward bias. And negative bias is applied onto the P side, which means a reverse bias. This is a kind of this sentence would confuse you a lot. So let's do this as short quiz. Say minus 2 volt is applied to the N side and minus 1 volt is applied to the P side. Then can you say that this PN diode is forward biased or reverse biased? Which one is correct? Well, the minus 1 volt is applied to the P side. So, wow, negative bias is applied to the P side, then definitely reverse bias. But another student said, no. N side is now minus 2 volt. P side is minus 1 volt. Which one is higher? Yeah, definitely minus 1 is higher than minus 2 volt by plus 1 volt. So forward bias is applied across PN diode. Who is right? Yes, second student. So always compare against the voltage applied onto the N side, how much voltage has been applied onto the P side. So you should always take into account how much voltage difference has been applied between P and N. Okay, so positive voltage is always indicates a forward bias. No, that sentence is definitely 100% wrong. Okay, so going back to the, now we have reviewed the physical meaning of forward bias and reverse bias. Now the job that we have to do in this lecture note is how to draw the NH band diagram under forward bias, under reverse bias. Okay, so herein I'm going to use a 0 volt as reference voltage so that positive voltage indicates a forward bias and negative voltage indicates a reverse bias. Okay, and last semester I have taught you how to draw the NH band diagram under a certain amount of voltage has been applied across a certain system or certain device such as transistor, MOS, capacitor, diode. Herein, take a look at the how much energy difference has been applied between Fermi energy level on the P side and the Fermi energy level on the N side. So here you can see that energy difference that is corresponding to the unit charge Q times applied voltage VA. So why I have always using a small q as a unit charge herein? Yes, the y-axis indicates energy of electrons, so the unit is electron volt. So instead of VA, I'm always using Q times VA because to meet the unit or to have the same to have the right unit onto the NH band diagram. So Q times VA has been applied, and here in the P side, the Fermi energy level is lower than the Fermi energy level in the N side, which means your minus y-axis direction indicates a positive voltage, because if you cannot understand how come these two physical meaning physical uh, physical quantity indicates a different direction, opposite directions. So always think about this equation. Electron's energy is defined as minus q times potential or voltage V. Okay, so take a look at minus because we're talking about the electron, which is negatively charged particle. Okay, so whenever you are looking at the energy band diagram, the minus y-axis direction indicates a positive bias. So now the PN diode is under forward bias. Certain amount of positive bias has been applied onto the P side by maybe Q times VA. Okay, so that is the main reason why the Fermi energy level on the P side is slightly misaligned with or to the Fermi energy level onto the N side. Okay, so EFP minus EFN indicates, this energy difference is corresponding to the Q times VA. Okay, all right. Then physically, what would be happened within the depletion region or the near the PN junction? Okay, so I'm talking about this area. Let me raise. Where is it? Okay, so what kind of things would be happened across the depletion region? So think about it. So as I have drawn the charge density block diagram, Coulomb per cubic centimeter, when with respect to the charge block diagram under at thermal equilibrium, a positive bias has been applied. Then the depletion layer's width, say W, has been shrink down. That means, on the P side, there are a bunch of abundant number of holes are available, and those holes, because of the positive bias has been applied onto the P side, so many holes are uh, diffused toward N side because the energy barrier height, this or that, basically Q times VBI, but now the energy barrier height has been lowered because of the forward bias. Basically, at thermal equilibrium, the energy barrier height for electron and energy barrier height for hole Q times VBI, right? But now, because of the positive bias, forward bias, the energy barrier height has been lowered by VA. So many holes would like to diffuse into the N side, so many holes would toward the depletion region. So the original depletion width should be shrink down because more holes are like pushed into the depletion region. Okay. Okay, what about the electrons on the N side? So as the potential barrier height has been lowered by VA, the electrons in the conduction band on the N side would like to push toward the depletion region. So this part compare against the depletion width at thermal equilibrium and the depletion width compare depletion width under forward bias. This difference or this area would be filled with more electrons because the electrons would see a lowered energy barrier height. Okay, so in terms of charge density block diagram here in rho versus x, once a positive bias, forward bias has been applied across PN diode, this area would be compensated with the electrons and that area would be compensated with the holes. Originally, this area has been charged because of the ionized donors, and that area was originally charged part because of the ionized acceptors. However, more holes and more electrons would get into this area, so that those areas would be neutralized so that the charged area would be shrunk down. Okay, what about the built-in electric field across depletion region? Yes, as you have guessed, under forward bias, because the depletion layer has been thinned down, the built-in electric field, the intensity of built-in electric field has been lowered and suppressed, and the electric field intensity, uh, the uh, in, range at which the electric field exists has been shrunken down. What about the reverse bias this time? Since energy barrier height has been increased, right? Instead of Q times VBI, now the potential barrier height has been increased by VA. Well, definitely this VA indicates that the magnitude of the voltage that you have applied. Say applied voltage is minus 2 volt, then I'm going to take a magnitude of it. Okay, so then you're going to understand that QVBI plus VA indicates a higher energy barrier height. And from the perspective of holes, this energy barrier height is Q times VBI plus VA. So since the energy barrier height increasing and increasing, so less holes and less electrons can diffuse and can exist near the depletion layer. So the depletion layer width has been widened out. So as shown in this charge density block diagram, under reverse bias, more region has been exposed, which means a more charged area has been exposed, and because of that, the electric field, built-in electric field, has been existed uh, at wider area, and due to that, the peak built-in electric field has been strengthened up. Okay, all right. So as we have done in the previous lecture, doing the electrostatic analysis, dE dx is charge density divided by dielectric constant of silicon, and here dB dx is equal to minus electric field E. So by solving those two different first order differentiation, you may derive the potential as a function of x. Then you're gonna draw these you know curves under reverse bias and forward bias. Then the last job to draw the energy band diagram under forward and under reverse bias is to flip over the potential plot. So why we should flip over the potential plot to obtain the energy band diagram E versus X? Because energy is defined as minus Q times P. So once you know how the potential plot has been drawn like that, then your energy band diagram would be this. Okay, so just flip it over with respect to the x-axis. Then you're gonna get this curve shape, and that is corresponding to this curve shape of in the energy band diagram. Okay, so uh, next week, in the second week, I'm going to get into some more uh, quantitative analysis to get to the current voltage characteristic of PN junction diode. So if you're not fully ready to understand and figure out what I'm going to tell you, so please review what we have learned in the spring semester, last semester, okay? So please do that. And if not, please read the chapters 5 in BRS book, then you would be okay. Okay, that's all for today's lecture, and see you in the second week. Bye bye.